Okay, so give me a second. Okay. Good morning, good afternoon, or good evening, depending where you are. Welcome to ICANX Talks series, a scientific forum aiming at connecting the world and the universe. Today, it's really our pleasure to bring many distinguished scientists and guest speakers. First, I'd like to introduce myself. This is Nick Fang, Professor of Mechanical Engineering at MIT. And I will serve as a moderator of today's seminar, as well as the panel discussion. And over the past months, or actually during the month of October, we had several distinguished guests who presented their scientific research at this ICANN Talks seminar series. And today it is our guest speaker is Professor Zhongqun Tian from Xiamen University. And what we will hear is first a 1 hour speaker presentation provided by Professor Tian. And it will be followed by half an hour panel discussion with several distinguished scientists who you will hear their insight about their own scientific career, as well as challenges and needs in the frontier of science. Without further ado, let me introduce our distinguished guest, Professor Zhongqun Tian, for this seminar. Professor Tian is a professor of chemistry at Xiamen University in China. He obtained his PhD under the supervision of Professor Xiamen in electrochemical research at the University of Southampton in 1987. He later returned to Xiamen University and was promoted to full professor in 1992. And his current research interests include surface-enhanced Raman scattering, spectral electrochemistry, plasmonics, and nanochemistry. He was elected as a member of a Chinese Academy of Sciences, as well as the RSC Fellow in 2005. And he is also a distinguished fellow of International Society of Electrochemistry in 2010 and fellow of the World Academy of Sciences in 2014. He received many awards from ICE, USA, UK, and many more. He's currently a director of Fujian Science and Technology Innovation Laboratory for Energy Materials, the immediate past president of the International Society of Electrochemistry, and he also serves as many on the editorial board of many international journals, including Matter, Checks, and so on. Without further ado, Professor Tian's talk today will be focused on nanoplasmonics. And Professor Tian, the podium is yours.
You see my slides?
I can see that you started screen sharing. Here we go.
Great. Thank you. Thank you very much, Nick, for the kind introduction. And I would like to start by thanking the organizers, especially my friend Alice and Zhang for the invitation. It's really my great honor and pleasure to give a talk at this ICANX Talks platform. And as you can see, my title has been modified a little bit. by emphasizing the molecule, because I'm chemist, but my background is physical chemistry. So I think that I would like to discuss with you on this my scientific research in the past 3 to 4 decades. And generally speaking, we are familiar with the term of plasma, surface plasma or surface plasma resonance. And they have the same scientific content. When the laser beam as the electromagnetic wave travel through the nanoparticle. And as you can see here, let me just find out. Okay. Okay, so that as a consequence, the particle can observe the energy efficiently if the wavelength is matching the resonance Raman, and surface plasma resonance. So the collective oscillation of conduction electron can be oscillated. And of course, this nanoparticle can be much more complicated. So that this is very interesting, because plasmonic can just afford photon, electron, and heat energy redistribution over time and space, providing lots of a chance for us. And we must say that surface plasma is one of, or plasmonic is one of a phenomena that can truly be described as a nanoscience, because it's not just the term of scale. It's really changed the properties. For example, if we change the size of nanoparticles from sphere to nanorod, and you can see the color change, you can see the peak of the, and the resonance frequency and intensity of plasma depends critically on many factors like nature of materials, size, shape, and more importantly, interparticle space. As you can see here, if we have two nanoparticles brought together, or we have a nano electron and close to the surface, we can just manipulate the light so that we can change the field and position. We can feel strength, local heat, and excited carrier. So it's very interesting and exciting. And as you can see here, if we have 10 gold nanoparticle with 50 nanometer diameter, then we have a Gaussian distribution for the instant light. But the nanoparticle can redistribute this light intensity energy into a very small hotspot. And I think that and it's really smart for this nanoparticle or plasmonic that can just redistribute those absorbed light then into this hotspot. Of course, it depends on the cavity, or we can say gap width. As you can see, this is the average of this instant light. However, after this redistribution, we can see light just focus or concentrate sharply at this gap of nanoparticle. If we try to just change, as you can see, the intensity of the light can increase from 0.5 milliwatt per micrometer square to 2,000 milliwatt, 2 watts. It's critical. It's really amazing. And imagine that if we have an instant light with 2 watts per micrometer square, then this gold nanoparticle will be burned or melt, destroyed. But now the light, the energy just go into this hotspot outside, just outside the nanoparticle. So it's amazing. And in order to just let you and get a clear picture, as you can see, this is a Bose field, very big. Then through this objective, we can just get a focus laser spot. It's about 1 micron to 200 nanometer. With this nanoparticle, then we can just further reduce this light and mainly concentrate at the gap, so that we can reduce it into 201 nanometer in diameter. Please just pay attention to this size, which is very useful for interacting with molecular science, because this is kind of size of molecule. Okay, so that roughly we can divide plasmonic into plasmonic physics and plasmonic chemistry. And of course, for plasmonic physics, it had started quite earlier from 1950s. But the plasmonic chemistry is relatively young. And because I'm physical chemist, so that my focusing just on 3 and correlated field related with plasmonic, either physics or chemistry. And you can see, and try to manipulate light in sub-wavelength dimension. And in order to realize some unique optical properties, as well as some new method and technology. So we should ask ourselves, how many ways that we can play plasma and molecule? Because they are interacting to each other. So that I would like to start just, and as you can see, this a very small spot is represent molecule. And of course, the red one is representing the highest field strength, which means we can create a hotspot when we reduce the size to 2 nanometer or 1 nanometer. And this molecule can be characterized and with optical or molecular spectroscopies. But today I will focus on Raman spectroscopy. Then we can also think about the field, a very strong electromagnetic field or light intensity may play a role for optical manipulation of single molecule. And moreover, if we want to get some chemical interaction, chemical reaction, we can also utilize this plasma as a mediator. The reason I'm calling mediate instead of and enhance is that sometimes mediator can change more precisely and more positive or negatively. Let's say we can increase the reaction speed or reduce reaction speed if need. So let's first go to the surface enhanced Raman scattering, because this is also a field that took me over 3 decades, and this is a very interesting starting point, because in that time, in 1970s, nobody knows what is the the plasmonic or even nanoscience, nanoparticle. We do not use that term at the time. However, people have already just get some colloid or rough surface, so that and found some very interesting behavior. So the story of discovery of cells indeed is very inspiring. But today that I will just give you some scientific clue about this surface enhanced Raman scattering, because as you can see, based on the textbook, nobody believes that Raman spectroscopy can be utilized or applied to surface science, because the signal is too weak. Let's take water. Surface water is essentially important for so many scientific fields. However, if you want to analyze this surface water structure and kinetic and structure related chemical reaction, is extremely difficult. Or it was considered impossible. However, based on the efforts of electrochemists, that the people try to study this electron and under electrochemical potential control, and try to just introduce the laser beam and to get the Raman signal. And to surprisingly, the source effect was just discovered, and that is really changed the field. As you can see, this is the rough silver electron. It's ill-defined disorder, but just based on this highly roughed surface, the Raman signal of water can be enhanced dramatically, which means that by utilizing source effect, we can study surface water, because the signal of surface water is equivalent to a million layer of water. So the signal is strong enough to be detected. So it's just make this field very, very exciting. Even people just consider this is the gift given by the God, because as you can see that the time for just claiming or to be recognized by the scientific community had taken 3 years or more, because people did not believe that this is true. But after that, as you can see, there is a time period that cells just going down, because there are some intrinsically limitation. I will go back to this point. After initiate of nanoscience, and the people found the way that we can just construct different kind of nanostructure, which just promote the different method related to this surface enhanced and Raman scattering. And I must point out that in the beginning of discovery of cells, people try to figure out what is the mechanism, because there are many theoretical models for the cell's mechanism in the late 1970s, such as the discoverer, Professor Van Dyen, first proposed that the cell's effect is related to electrochemical double layer effect. That's not correct. And it was Martin Moskowitz who firstly introduced the concept of a surface plasma contribution to cells and published this paper and in 1978. And he pointed out that this anomalous intensity arises from pre-resonance. It's not all resonance excitation of conduction electron resonance. In that time, nobody called us surface plasma, but this is truly the scientific content. In that time, he mentioned this nanostructure as a bump of from the metal, so that which means it's a rough surface. And I think this is truly most important, one of the most important paper that just have let the study go along the right direction. So that after this theoretical approach, in fact, there have been many theoretical approaches. We still not yet reach the final model or theories that can combine different effects together. But surface plasma is truly the dominant, most important contribution to the cell's effect. And because for the better understanding, I would like to just show you this slides and for a two-step of cell's mechanism. Because if we just simply correlate this normal Raman to the surface enhanced Raman, it confuses many people, many students. However, if we consider this is a nanoparticle with a hotspot, please notice that this is not correctly proportioned because molecule is much smaller than the nanoparticle. Nanoparticle is about 50 nanometer to 100 nanometer, and molecule just 1 nanometer or smaller. And as you can see, if we have a plasma resonance, so the nanoparticle can absorb energy and introduce into this hotspot, which means the light is much efficient because the cross-section of this nanostructure, including molecule, is much larger. So that the signal in comparison with this, the Raman scattering signal is larger because the light intensity, incident light intensity is much larger. So this is the first step, because the intensity is proportional to the field strength and in square relationship, so that we can see. Then the second step is about the emission, because a nanoparticle is so smart. In the first step, it just plays as an receiving optical antenna, and so that it can focus the light, concentrate the light. But for the second step, this nanoparticle again playing another key role as a transmitting optical antenna, which means that the whole system, including nanoparticle and molecule, are oscillated together. So with a certain frequency, which is in the region of plasma resonance, so the light can just emit it with a very strong signal. And this can just try, because some students were quite confused. They asked me, the light from molecule cannot go out because it's just hinted inside this cavity. They did not realize that the whole nanostructure just make this emitter as a whole, because nanostructure play the key role as an antenna. So this is a very interesting to let people understand Sorry, maybe I will get back. As you can see, because the enhancement factor, which is the source signal intensity comparison with the Raman normal Raman intensity. But we should realize that if the field, because it's the fourth order, if the field change about let's say 100 times, then the signal, the enhancement factor will go to 10 to the 8th. That is huge, right? So that with that, the people were very happy. But very unfortunate that in the early 1980s and all through 1980s, people gradually realized that the source of plasmonic active and metal or materials are limited in gold, silver, and copper. And moreover, that the surface science also did not accept the source. They complain, but for the structurally well-defined single crystal, and source cannot be used or for their theoretical modeling studies and simulations. So, but if we think about these two bigger limitations, the origin problem, I think, is due to that the source is a baby of menagerie of surface plasma and Raman spectroscopy. So it's just take some good or advantage, strength, but it's also a heritage, some weakness, which means that because of plasmonic, as we mentioned, that we need to have some free electron, and like metal, like gold, silver, and copper, they have a lot of free electron or S electron that can be oscillated and generate a strong surface plasma. But if we have this limitation, then source and just get some strength from plasmonic and get some weakness from plasmonic. And the strength of Raman spectroscopy is a spectral resolution or energy resolution, because we can then source have a very good spectral resolution as a fingerprint technique. So we can analyze many molecular systems. But the morphology generality for the Raman, well, if we do not consider surface Raman, it's excellent. For the material generality, of course, it's excellent. And so these are the things are very bad, and to just prevent further development of source, because electrochemistry, surface science, catalyst science community did not accept source. So how to overcome the problem is truly essentially important. So we have to return to nanostructure. We have to think about more about nanostructure. So in the past 3 decades, many groups, including ours, and we have tried to just change this ill-defined nanostructure to the better order structure, nanostructure. Then we just move forward to combine different materials, and in order to rationally design different nanostructure in order to overcome these two big problems. And of course, from my group, after returning from the University of Southampton, we have just tried to make some contribution from different aspects. And I'm very fortunate to have many good, excellent students in a different time period, and so that we can make a great contribution, at least to some extent, to overcome this two bottlenecks. And due to the time limit, I will just show you the last one: shear isolated nanoparticle enhanced Raman spectroscopy that was invented in 2010. And as you can see, that we just overcoat ultra thin silica shear onto this gold nanoparticle, which means that the molecule will not absorb at this plasmonic active materials, which means that we just have enhanced electromagnetic field. Then if we spread over this gold nanoparticle, which is isolated by the silica shear, so we can consider this is just as a sand. So it's very easy and to just go spread over into either single crystal surface, which have a structurally well-defined surface, or virtually any materials, because the enhancement antenna is from gold nanoparticle, but not from the substrate. And so by utilizing this strategy, and we can apply this shyness, we can just take this nanoparticle as to shine any material or to shine any surface, and to get what we want. So the beauty of shyness is that we can just explore the capability for the source, but now we can not call it a source because the molecule cannot absorb on the surface of plasmonic active nanoparticle. So we just create or make a new branch of plasmon enhanced Raman spectroscopy, plasmon enhanced Raman spectroscopy in short pairs, and include at least 3 branch: source, shyness, and tipping enhanced Raman spectroscopy. And so that we are really happy that we make some contribution for that. As you can see, with shyness, we can study different single crystal. We can study carbon monoxide on platinum, which is very important for catalysis or electrochemistry. And we still can get the enhancement factor from 10 to 4 to 10 to 5. So as you can see, these are the different single crystal phases, and because CO can absorb on different sides on top or bridge, so that we can clearly distinct those phases with a different structure. So that's what the surface science wanted. But for the needs of electrochemical or energy field or catalysis, we apply shyness to the oxygen reduction reaction, and those are on platinum single crystal surface. And of course, Zhongqun Li is a student, PhD student, and he has made a great contribution to this discovery of shyness. But now he has an independent group and continue to move forward to bring shyness into these different applied to the field. But I'm really interested on this one because as surface water is so important, so that it's just shyness have brought an opportunity, new opportunity for us to understand or to classify the orientation change with the applied potential. As you can see, when we change the applied electrical potential, and the shyness spectrum change dramatically, which just provide a hint and also related with the DFT. That's Professor Jin Chen's specialty, expertise, so that they work together and so that they can clearly identify the orientation of this surface water. And recently, they also extended this study from platinum to palladium 111, and with joint work with Professor Feng Pan of Peking University. And this paper, and I cannot just mention more because it's just accepted by Nature recently. I guess maybe in the very near future, you can see this article soon. So that, okay, so let's go to more practical or your market-related application. As you can see here, plasmon enhanced Raman spectroscopy can be applied into the different fields, including COVID-19 detection. And if we want to just put them together as a one common feature, that is source or shyness can be applied to fast detection of trace chemicals from various complex systems. So this is truly very exciting, but I must say that for each application, we have been just working very hard because sensitivity is always very important. It's essentially important. If we utilize shyness instead of bare nanoparticle, and the intensity decrease to 1 or 2 orders, that is not what we want. So how to bring it back is very important. So we propose the third generation of phosphor with hybrid nanostructure, which means that we try to just apply these studies, not just only on those metal systems, but also go to semiconductor or polymers, or even some live and living life cells, and any kind of a system that we all very interested in. But we are facing different challenges, but that is the kind of interesting for science to overcome. As you can see here, we try to get rid of this coupling, not just only from the those particle coupling and particle substrate coupling, because for some systems we need just have a single particle. Can we realize it? And of course, this is a big challenge. But we just have some simulation and found out that if we change the shell from to some high refractive index, and for example, this gallium phosphate, then we really can just improve the enhancement factor to reach 10 to 6. The fourth to silicon or other semiconductor. And that is very excited because we really want to bring this pulse or source or shyness to our colleagues from different fields. And of course, we also should pay attention on the optical assignment. It can also bring us some extra or additional enhancement by 1 order or 2. So that I have no time to just give you those details. But what I point out is that we need to just think about deeply and try our best in order to get the best outcome. And as you can see, if we have a plasmonic, it's a plasmonic involving molecule, it's getting very complicated, but very interesting, because traditionally we have interaction of photon with molecule. There is a molecular spectroscopy, including infrared and Raman and other molecules, fluorescence. And if we have this molecular absorbed on nanostructure, we have a nanosurface science. And if we have a photon interaction with a nanostructure, which means we have a plasmonic. However, for this plasma enhancer, Raman spectroscopy or other infrared spectroscopy, then we just get these 3 bodies issue. And how to work, not just precisely, but synergetically, then we possibly can optimize the pulse activity in the near future. So let me just move on to the second part, which is the second question we ask ourselves. Can we just make a contribution to the single molecular optical tweezer, or we can optical manipulate the molecule? Because for here, we just characterize our molecule. But if we can manipulate, if we can trap and release those molecules, so that we have a higher capability for our studies in both fundamental and application. Okay, so I always like to go back to the starting point, or to get a comprehensive picture of the new field. And as we can see that, in fact, we have found that there have been 5 methods for this molecular tweezer. However, unfortunately, because it's so difficult for just a control or track very small molecule, so the people use either AFM or STM tip for binding molecule. Then they just make some manipulate. And they can also use, this is AFM, this is STM, and this is utilize magnetic field to control it. And we are most interested on this tool because it's related to optical trapping. And for these optical tweezers, so far people utilize dielectric microsphere, which means it's in a scale of a micrometer. Then they, of course, this is not correctly proportion for this molecule and this microsphere. And so that the optical field can be applied easily onto this dielectric microsphere, so that they can bring this sphere out and in. But if this sphere has some molecule binding into this sphere, so it can be controlled. And this is one way, and people have to utilize this microsphere, which of course is not satisfied. And on the other hand, this is from biological field, the people have done so. And on the other hand, the physics utilize ultra high vacuum and low temperature. And so they try to manipulate or trap this by the strategy of laser cooling. But because the laser cooling has a big limitation, so it's easily control item or very, very small molecules, such as 2 items as a molecule. But once they go up into this part, it's really hard. And so that as we noticed that in 1997, Nobel Prize just gave this scientist who just introduced this laser cooling optical tweezer. And on the other side, the optical, the Nobel Prize was awarded to the people who invented this optical tweezer. But there is a gap still. So what is the best way to fill in this gap is a heavy challenge so far. And of course, we in the 10, 20 years ago, we already noticed that in theories, like Sunny Xie from Harvard University at that time, and together with other groups that predict that the surface plasma can be used or applied to trap single mode. But in theories, after that, we just haven't found that any successful report experimentally. So that we try to just take our strengths or advantage in another field that's called mechanically controlled break junction, in short, MCBJ, because MCBJ has been widely applied for or as one of the most powerful methods in single molecular electronics. So that as you can see, they just have 2 nano electrode. I mean, at the tip, it's a nano size. So that if we have a very thin, like silicon wafer, or we can just have other that is with a material that can burn, that can just make this gap big and smaller by just moving up this actuator into along this direction, so that with this ratio, in fact, this the judgeable gap can reach about angstrom or even sub-angstrom. Because as you can see here, if we just move up by 1 micrometer, so that it means that because of this reduction ratio, we can reach 1 angstrom easily. In Xiamen University, we have a very strong group led by Professor Wen Jin along this direction. And I myself have already applied this field and interest in MCBJ about, I can't remember, maybe 15 years ago, to obtain the first source spectrum from this MCBJ system. And of course, my MCBJ is not as good as that Professor Wen Jin one, and together with Professor Yang. So that we just work together. I have a very excellent student, Zhang Chao or Chao Zhang, who just take this joint project as a leader. Truly, he is a leader for this approach, Zhang Chao. So that I'm very pleased that by joint work and collaboration, we have been able to realize that we can just trapping not only molecule into the hotspot, but we can also measure the conductance of this single molecule, because we can distinct if it is a single one molecule or it's a 2 molecule all three molecules because it's very sensitive for this electron conductance measurement. So that as you can see, these conductance, this step representing single molecule. Okay, so that we know if we have a light on, we can comparison with a dark condition, or we can comparison with another laser with a different wavelength that is out of a resonance of surface plasma. So that it's clearly indicate that with a correct instant wavelength, we can get this conductance of a single molecule. And this one is just a tunneling current, this one. As you can see, for the blank condition, we do not have any signal from molecular conductance. And if we reduce some molecule, but in a dark condition, we can get this, the molecule, of course, can get in and out without light optical trapping. However, if we have corrected wavelengths of instant, this probability has been increased dramatically, which is quite exciting for us. Of course, we also make some simulation by Dr. Also my former student, Jin, and he is an expert in this part. So that as you can see, we can really provide some simulation result to confirm that this is the good and this is a good approach for this one. Moreover, we try to see if we can just trapping and release not only one kind of molecule, but two kinds. Can we distinguish? Because it's very important for the real application. So we introduce two types of molecule with, as you can see, the length is different. Of course, which means polarizability or the volume of this molecule is different. Then in the dark, we can see that we can see the two conductance value representing these two. However, if we just make the light on with a correct wavelength to have a plasma resonance, we can get this clear distinctly different probability, which means that it's possible for us to selectively trap the different molecule. I must say that this is still far away to go. It's just a very preliminary approach. And we are very pleased to just see this very new publication from Katrin and Dong group that they use a tip and to study a similar system. And as you can see that with a light on or laser off, this retaining time is very different on the for this system. The junction formation through this molecule has a different time. It means that the plasmonic may play an important role for increase this magnitude in about 1 order of maintaining time for the single molecule measurement, so that it's just give us a more support to move on along this direction. Due to the time limited, I must go to the third approach that our group has been done. in this along this scope and framework. That is a plasma-mediated chemical reaction. So that this is just give you some picture about difference from plasmonic spectroscopy to plasmonic chemistry, or from plasmonic physics to plasmonic chemistry. If we consider chemistry, it means molecule has changed its structure and it will create a new molecule. So that we change from molecular spectroscopy to photochemical reaction. Excuse me. And we change the nano surface size to those nano electrocatalysis or nanocatalysis. Of course, we keep this nanoplasmonic and as the same. So what happened? And should we just can we just take some effort along this direction? Of course, as I mentioned, if we change from plasmonic physics to plasmonic chemistry, in fact, we all consider this 3 resolution at the same level without change. But we really change the probability. For the Raman scattering or other spectroscopies, we are considering this intensity, spectral intensity, which of course is also related with the probability. But now we are very concerned about this reactivity, probability of chemical reaction, which is very new. So that we know that physics always think about relation. So if we want to use one word to describe physics, and relation could be the right term, because we all have different physical parameters to form different equations. But chemistry is much more difficult, because it's the word we would like to describe chemistry is change, which means we have to face much more complicated system in comparison with plasmonic chemistry. As you can see here, for this plasmonic physics or plasma enhanced Raman and also with enhanced Raman, you can see these trends. But as you can see the time that just from 2010, we have some limited publication, and it's and I would also like to compare with this way. In fact, after discovery of SIRS in 1981, and Louis Bruce from Columbia University just proposed this theoretical model for this enhanced photochemistry. But the development is very slow, and many groups just try to figure out, including our group. But it seems that we have to first carefully think about some key questions on plasmonic chemistry. Has plasmonic chemistry has its own scientific connotation or unique advantage or scientific content, which cannot be included in the conventional surface photochemistry or nanocatalysis or thermochemistry. Otherwise, there's no need to create this new concept or new terms. And what are the fundamental issues? And what are the development next for this plasmonic chemistry? And of course, as I mentioned, plasmonic chemistry is very complicated. So we have to understand synergetical effect, and including these all factors. It's far way to go, but we have to move on so that as we can see here, we are presenting three factors: energy factors, time factors, and spatial factors. So with we all have to consider carefully, and in order to get a full picture. We have realized that maybe one of the most important factors is that we need to have have some way to generate long-life energetical carrier, just like hot electron and hot holes, because plasmonic nanostructure or based on this plasmonic physics, we can see that the lifetime is much shorter than semiconductor-based and photochemistry. So that although there are several good advantages and strengths from plasmonic nanoparticle and nanostructure, we have realized, but we found just like SIRS, and in the beginning we thought it's wonderful and everything is great, but we realized later there are some intrinsically limitations. I'm feeling that this field seems also go into this stage, so that we have to work hard in order to take some advantage of nanostructure, which means that we have to make this not just simple gold or silver nanoparticle. We have to just implement some semiconductor or catalyst metal oxide for realizing this important reaction with a high efficiency and high selectivity. Nick, I'm sorry that I have just reached the time. Can I have a few minutes, or you want to stop me here so I can just go into the last maybe 2 slides?
I think with permission of the organizer and panelist, Professor Tian, please go ahead and try to finish your talk in the next few minutes.
Okay, so that I will skip up this one because it will give us it will take me some time, but it's really interesting to see this plasma-mediated chemical reaction can be realized to some extent, I must say. But these are some very interesting phenomena that nano-confined thermal field together with hot electron and hot hole that we really can go, because of these nano-confined reactors. It's different from those nanotube or some cavities and that confine the movement or mass transportation. This is an open field, and so the molecule can come in and go out, which means that we can possibly have a high yield for the but this is one key question. It's not a summary, but it's a question to all audience. And you possibly are more brave or more smart than us, so that you can think about all these questions that just influencing the plasmonic mediated chemical reaction. I just give these 2 key questions, which I have already discussed with you on these mediators issues. And of course, we need to keep thinking and enjoy exploring a new plasmonic or scientific field and try to, but for understand this, we should try to deeply understand the origin and mechanism of each process so that we can rationally design the corresponding nanostructure. So I must thank my students, and as you can see, I only can list a part of my students who made a great contribution to this three approach, and my collaborator at Xiamen University, and my PhD supervisor, Martin Fleischman, who led me to the this field in the beginning, but very, very much appreciate his guidance. And of course, international collaborator and domestic collaborator. With that, I thank you very, very much for your attention. And I'm pleased to discuss with you. Thank you.
Thank you very much, Professor Tian. Really appreciate your talk. With that, I'm pleased to introduce the panelists who are part of our panel discussion today. So please give me 1 second.
Okay, so I will stop sharing.
Yes, please.
Let's see. I'm just gonna find out where it's. I think you have already get in.
Okay, excellent. Thank you so much, Professor Tian.
Okay.
And yeah, it looks like on our screen, we already see a couple of distinguished panelists and participants of today's panel. The first is Professor Ryan Jin from University of Texas at Austin. So Professor Jin's research group focuses on innovating optical manipulation and the measurement of nanoscale biological and extraterrestrial work. Professor Jin received many distinguished honors, including the 2020 IEEE Nano Best Poster Award, 2019 University Co-op Research Excellence Awards, and the 2017 NIH Director's New Innovator Award, and many Young Investigator Award, including the 2014 Beckman Young Investigator Award. He is elevated as a Fellow of the Institute of Physics and a Fellow of the Royal Society of Chemistry. We also have honor to introduce, let me see, to my screen. Professor Xiamen Zhang from the University of Hong Kong. Professor Zhang just joined the University of Hong Kong, the Department of Electrical and Electronic Engineering. And before that, he was at the UCLA and obtained his PhD at École Polytechnique, University of Montreal, Canada. And at Hong Kong University, Professor Zhang is guy who lead a research group on the wearable, intelligent, and soft electronics. And he developed the world's first stretchable organic electrochemical transistors and demonstrated an early prototype of fully integrated soft optical electrochemical transistors for wearable healthcare applications. Professor Zhang is a featured scholar of the Global Medical Wearable Forum of 2020, and he is recognized as a top reviewer by Advanced Functional Materials, Advanced Electronic Materials, and Organic Electronics. He's a recipient of also many prestigious awards, including Vanier Canada Scholarship, the Outstanding International Students Award from the government of Quebec, and the Chinese government award for Outstanding Self-Funded Student Award from the government of China. And last but not least, Today, we have also a distinguished ex-challenger, Professor Jing Do, who is a distinguished research fellow, PhD supervisor, and also a member of the overseas high-level talent program. Professor Do is currently at the School of Material Science and Engineering at Peking University. Before that, Professor Do received his PhD with Professor Jian Pei at Peking University, and he also spent quite a few years with Professor Marcia Dinka as a postdoc fellow at MIT. So Professor Do will be our first speaker during the panel section to raise his questions and initiate the conversation. Without further ado, Professor Do, the podium is yours.
Okay, thank you. Thank you, Professor Tian. It's a really nice talk. I really enjoy it. So I have two questions. My first question is, search, and especially single molecule search techniques, are highly sensitive analytical tools. The high sensitivity can be an advantage, but it can also be a disadvantage, especially when these techniques are applied in complex real-world samples. You can imagine that there will be complex competitive absorption or some non-specific contamination during the measurement. So my first question will be, are there any strategies to overcome this issue?
Yeah, this is a great question. Thank you, Professor Do. And as I mentioned, that search is challenging on those fast detection of trace, including single mark, from complex system. So that these are the target that we are challenging. And of course, it's not easy. And as you can see here, if we are talking about the gap or cavity of 1 nanometer to 2 nanometer, and think about that, those gold items are mobile on the surface. If we have one item move in or move out, then of course you can see the gap is changing. So that is one of the reasons that we go on to the shiners, because with a shear protection, so that the gap is more stable. Otherwise, you are absolutely right. For the single molecule, we need a very high sensitivity, which means we need a very small gap, maybe smaller than it's 1.5 or 1 nanometer. And of course, if you decrease to less than 1 nanometer, we have another problem about tunneling issue. And as you can see here, if we wanted to get those single molecules, we are thinking, or we have to just try to have like a silica share, but together with some molecule, which means that we have a polar silica here. Of course, this silica share is very, very thin, so that we have some defect. And we can take this disadvantage to be an advantage. We can introduce some link, which can selectively link the molecule we are interested in. And so that even from some complicated system, and we still can selectively pick up those molecules that and measured also with a relatively high stability. So this is the answer to your question, but I think this is not fully satisfied answer. But this is a great question. It's it's take a lot of time from many groups, but this is the approach we are aiming to.
Yeah, thank you for your answer. So yeah, my last question is, I like the name Signer. It's really signing name. So my last question is about this field. So it's really exciting to see Signer or other search techniques can even detect a single molecule. I'm curious about that. If we can, if we can extract other information beyond the single molecule. I mean, for example, some aggregate state information, some morphology on the surface, or some conductivity, semiconductivity. Can we do that by using this technique? Yeah.
Yes, you are right. And this is also a very important question, because we can have for the Raman spectroscopy source in the shyness, we detect molecule. However, that if we do not want to detect molecule, but we want to detect defect or surface properties of semiconductor or other materials, we can use probe molecular strategy, which means that we can selectively take some molecule as a probe to study different surfaces or even defect. And this, in fact, is one of examples. As you can see, CO is a probe molecule. Then, and if we just provide this CO to different surface with different phases, like platinum 111, 100, and 110, and you can see that CO is so sensitive. And if we change this platinum into other materials, we can selectively choose the proper molecule. We maybe keep using CO, but we can also use some molecule that can provide some additional extra information related to surface science, catalysis, electrochemistry, semiconductor, IC industry, so on. So and it's a really interesting question, and of course we can also have not just a single probe molecule. We can have 2 or 3 kind of molecule. Then it may provide some synergetic effect. It may provide some more complicated information on the surface or ultra thin film, which is very important for physics or industry, and that could be also an important approach. But we have no time to carry out these studies.
Yeah, thank you for your answer, Professor Tian. Yeah. Nick.
All right, thank you very much. I'd like to give our distinguished panelists, Professor Zheng and Professor Zhang, to also have a question or a conversation with Professor Tian.
Thank you, Professor Fang, for the nice introduction. Hi, Professor Tian. This is Yue from UT Austin. This is fantastic. So in your third part, you mentioned that actually in your chemical reaction, you have several effects from the plasma excitation at the middle nanoparticle: electromagnetic, thermal, even carrier tunneling. Can you also comment how these 3 facts, in particular the thermal and the tunneling, affect your second project in the single molecule tweezers?
Well, thank you. This is also a great question about this study. As you can see here, we have when we have a plasmonic active nanostructure, then we know that when we excite, get this. Let me see. This might be a more clear. as you can see here, that we have this molecular on the nanostructure of plasmonic systems that we introduce molecular in a hotspot, and we can see because of this. Let me see which one is the best. Because of this, let me. Oh, I did not show. Okay, let me keep this. And as you can see here, we have a hot electron and hot spot and hot hole and generated. However, if we want to go to from the third approach to the second approach, and we must take care of this chemical reaction. I should say that in the early stage of third study, we have already observed some actual peak during our study, which is related with the chemical reaction. But we thought these are the negative part results, so that in fact from chemical reaction, they are positive. And if we study this an optical tracer, I don't think it's so easy to get a chemical reaction. As I mentioned, you wanted to change a chemical reaction. That is not easy at all. Here, when we get this hot carrier, but the lifetime is very short. Lifetime is very short. And moreover, as I mentioned here, we need to have a time match. We need to match time. Because the time is different for the thermal and for the hot electron and for the field. And we can distinguish by utilizing the power laser so that we can distinguish these three effects. And if we want to go to the optical trapping without this additional catalysis or semiconductor to keep this lifetime up to 1 picosecond or longer, reaction yield is very, very low. It's very, very low. Moreover, that we are mimic the light intensity. I mean the sun daylight intensity, and that is important. If we cannot utilize the laser to make a chemical reaction, nobody will accept this one. It's too expensive. So the approach we are making is very realistic, and even though that we put this plasmonic chemistry as the last one, is that we are trying to find the best path to overcome this problem. But we already get some, but that is a quite selective or limited molecular system, which is very completely different from the system we are utilizing for the second part, optical tracer. But we must pay attention, as you point out, which is important when we carry out this trapping and studies, that we need to consider the possibility of chemical reaction. Thank you. Thank you for your point. Good point.
Thank you. I know our time is very limited, but before I pass to Professor Zhang, I would like to hear your advice on, as a group, how you sustain the innovation for so many years.
Well, this I learned from my supervisor, Martin Fleischmann. He is a great scientist, and so I very much appreciate his guide. He always very, very creative, and he has an excellent mathematics and physics background, and he have to encourage himself, because so many people disencourage him for some crazy idea. And so that I learned from him, because he told me that do not blindly believe those authority. Otherwise, you will be just hit down, and you have to be brave. And so that is what I'm doing, and that is what our students are doing.
Thank you very much. That's all my questions.
Thank you very much.
Yeah, thank you, Yuebing and Professor Tian on this stimulating discussion about the scientific career as well as the great challenges faced ahead of plasmonic enhanced chemical reactions. I'd like to give Professor Zhang the podium to ask questions or comments.
Thank you very much, Professor Fang, for the introduction. And thank you very much, Professor Tian, for the very inspiring talk. And I can feel, it's the first time I've met Professor Tian, but I can feel you are very humble and also very knowledgeable person that is really on the frontier of this field. So I'm a little bit out of this field, but I have a very applied question because I work on a kind of electronic device, semiconductor device called the electrochemical transistor, and where we have semiconductor channels that use the conducting polymers, and the electrochemical reactions will happen on the conducting polymer to change its conductivity. So I'm wondering if this technology, the plasma-mediated chemical reaction, can help to trigger a local electrochemical reaction on the conducting polymer channel. So do you have some comment on this topic? Thank you very much.
Yeah, this is a very interesting question. And I'm afraid that I may not just get a good answer to you, but I will try to. And thank you very much for your kind word. First of all, that I'm thinking, based on this new new electronic system, and involving some conducting polymer, which of course is a new direction. I think that you are also very brave to take this challenge. And of course, there are many limitations. And if we can probe, or I think my two approach may all fitting your request. One is that how to characterize those systems, because it's quite small and it's a submicron or micron system. And if we have some good system that really can help to during your process or in the beginning or after, that you have some tool that really can tell you and what's going on before and after, and what's changed in terms of structure. And that plasmonic enhanced molecular spectroscopy may be good, because shyness, for example, is a good way, because it's insulate. It will not just make some additional influence or effect to affect your structure or your process. So if the shyness can be well controlled, this is just a cartoon to tell you how simple shyness can work. However, you can think about if we have a rationally designed to fix your electronic structure, then we can. It's better than tipping enhanced Raman, because tipping enhanced Raman have a kind of a bigger tip that may just get one spot. However, for the shyness, it's I'm thinking there is a possibility to give you some provide some additional and tool and to understand your system. For example, these are semiconductor, or you can consider this as a conducting polymer, for example. And moreover, that if you want to introduce the third approach we are making, then you can introduce some chemicals, or you can even utilize this to just create some so-called defect or change of chemical structure. But I'm not quite sure which kind of condition that is better for you. You can either change the wavelength, change the temperature, and change the chemical structure, or even you can introduce some chemicals by just binding those nanoparticle into the position and the right position you are interested in. But I am a little bit worried about this chemical, the efficiency of chemical reaction, just as I replied to Professor Zheng, and how to just generate a really highly efficient chemical reaction that can provide this processor, because you must need this one for your fabrication. I'm sorry, I may not provide you a good answer. It's just my instinct, just some very brief, mature thought.
Thank you very much. It's already very clear. Yeah, thank you. Yeah.
All right, thank you. I think we just heard of very stimulating feedback from Professor Tian. I had a lot of questions by myself, but for the interest of time, I think we should rather conclude the session. And I wanted to take the opportunity to thank all the panelists, as well as our guest speaker, Professor Tian, for the great discussion. And as a token of appreciation, I wanted to present online a virtual certificate from the organizers of ICANN. If I was able to show this. Thank you, Professor Tian, for the scientific contributions and insightful discussions from today's guest lecture. Here, this is just a certificate celebrating your achievement, and thank you for your participation of the ICANN talks.
Thank you so much. Please just send me by email or WeChat, and I will keep this. And thank you, Professor Fang and Professor Zhang, Alice, so much for the invitation and very good discussion, which I really like it. I like a challenge and some unknown, unexplored scientific issue and topic. So, which I really enjoy very much. Thank you. Thank you all so much.
Thank you. And with that, my task is to also advertise the upcoming ICANN seminar and presentation series. On next Thursday, Professor Nicholas Pappas from UT Austin will join Professor Hui Wang as the guest speaker of next ICANN X story series. And on Friday, we will have the inaugural series of ICANN talks of November with Professor. I'm sorry, I'm not able to read this on my slides, but we will have a new series of talks led by a few guests from European universities as well as Iowa State University, and please watch November ICANN talk series and mark those on your calendar. You will have a lot of new scientific talks as well as guest speakers that are coming. with that, I'd like to thank the organizer, in particular, Professor Alice Zhang from Peking University, and many friends and sponsors of the seminar series. And I really thank the audience for your participation, and we look forward to interacting with you in the near future. Thank you.